It is an alpha particle or smaller, so I guess I'll let it slide. All right, and then next to that one, we have an alpha particle that we are hitting, what is that, radium?
Yeah, we do.
We're hitting radium with, and then I think this is trying to show that we very temporarily have a thorium-230, which is unstable, and then does beta decay to turn into palladium?
It's weird. It's protactinium.
Protactinium?
Yeah.
PA is protactinium?
Yeah.
Okay. It turns into protactinium and a beta particle and an antineutrino. So as long as I think that protactinium-230 is like a viable isotope, then I'm probably pretty happy with that. And the average atomic mass of protactinium is 231. So yeah, I think that that works absolutely fine. And I'm very happy that I saw the antineutrino along with the beta particle. All right, we have a few more we'll take a quick look at. Here we have alpha that is hitting a neon and then producing a proton and a sodium. The charge numbers definitely balance, the mass numbers definitely balance, but proton decay is not one of our typical types of decay. So I'm kind of just not happy with it for that reason. Sodium-23, do I like that? Yes, that's actually very standard sodium. The average atomic mass is 22.990, so that would be probably the most abundant isotope of sodium. All right, here we have mercury that we're inducing a transmutation by shooting an electron into the nucleus. And then we're getting gold and gamma photon. We just want to move the zeros over to the left. That looks fine, but is gold 200 realistic? Yeah, so 197 appears to be the most abundant isotope, so 200 seems fine. So yeah, the alchemists would be jealous of inducing that transmutation. Yeah. All right, and then we have, it looks like a very similar one over here. We have an electron hitting a fluorine-19 nucleus. And it looks to me like our charge number does balance and our mass number does balance, but boron decay and lithium decay are not one of our normal types of radioactive decay, so I probably wouldn't consider that an induced transmutation. I said this to one of the other groups kind of right before we started going over this. This would probably more closely resemble fission, and we do end this topic with a pretty thorough quantitative analysis of fission and fusion, so we should make sure that we get that distinction once we talk about those processes. All right, so it looks good. Looks like we are able to balance the nuclear reactions for sure, and it looks like we get that an induced transmutation is jamming something into a nucleus and forcing it to be unstable that way. Any other questions about this unnatural decay, this induced decay? All right, fantastic. Okay, so our next objective was a defined objective, and it is my least favorite definition of the whole file, I think, and it is to define a unit of mass that is pretty standard when we're talking about individual nuclei. All right, so we need to define the term unified atomic mass unit, and then there in parentheses, there are a couple other units for mass that we want to be able to work with. All right, so the unified atomic mass unit is 1/12 of the rest mass of a carbon-12 atom, unbound carbon-12 atom. Ugly. Well, ugly, but if we can remember carbon-12, then fine. Then we're always going to be able to at least recognize the definition. Right? So the unified atomic mass unit pretty much sets the mass of a neutron and a proton to 1, and that's really convenient. It's really convenient. It would be very helpful for us to open up our data booklet to the page that has the constants on it, right, where we can find the mass of our neutrons and protons and electrons. because we do have a conversion factor. I think it's right on that page to get from some of these units of mass to others. Yeah, right at the bottom, right? It says quantity, unified atomic mass unit, and then it gives us the approximate value in both kilograms and some other unit that we're going to deal with in a few minutes, right? So we do need to know the definition, but in practice, right, the conversion is there, right, to get us into this unit or away from that unit. So before we move on to our next objective, let's just go ahead and see if we can convert 2 kilograms into atomic mass units, right? The conversion factor's there at the bottom. So give you a head start, and then I'll do it myself. Do you have your keyboard? Yes, you're gonna need that. Do either of you have it? Yes, yes.
How many zeros? That's a lot of zeros. 6.
Bless you.
It's huge, right?
Yeah.
Huge. Right, these atomic mass units, the intention of them, again, is to set our nucleon masses to approximately 1. So 2 kilograms, and that is just a huge number of nucleons. So when I do this, I get, let's see, the conversion factor has 4 significant digits, so that's what's going to limit me. 1.204 times 10 to the positive 27 atomic mass units. That's just an immensely large number. Justin.
So is that like the amount of units of like that in 2 kilograms? So like, actually, yeah, I answered my question.
Okay. Well, what was your question?
It was like, alright, is that the number of like how many like 12ths of the carbon-12?
Yeah. So let me think about this for 1 second before I answer. Well, order of magnitude. Yeah, I don't know. That question hurt your brain, and it's hurting my brain too. All right. So we are going to use this unified atomic mass unit, but it's actually not my favorite unit of mass in this topic. We'll get to that, I think, on the next slide, or maybe the one after that. Our next objective involved applying Einstein's mass energy equivalency equation. And we've actually never really used that, at least in our physics studies here. I'm sure you've heard of this E equals mc squared before, but it's the only equation in topic 7 for your data booklet. I hope we're familiar with the 3 terms. So the E does stand for energy, right? The M does stand for mass, and then C is our speed of light squared. So the kind of importance, large scale, of this equation is that it does tell us, it does recognize that mass is a kind of energy, right? Mass is a form of energy. We can interconvert from mass to other energy, right? And then back to mass if we want to. One example of this, which we mentioned this the other day, but one example of this is our PET scans. I think we referenced PET scans when we talked about positrons a class or 2 ago. So in a PET scan, and we're gonna, actually I'll get my speakers out while I talk. I have 2 videos, we're only gonna watch the shorter one. In a PET scan, we put a positron emitter into a patient. All right, so something that does positron decay. And when the positron decay occurs, that positron will interact with regular matter, like an electron. And then when we have matter and antimatter, like meat, all of that mass gets destroyed and gets converted into other forms of energy. So in the PET scan, right, we generate positrons. Pretty much as soon as that positron is generated, either gamma photons or X-ray photons are, well, all of that mass is destroyed, and gamma photons and or X-ray photons are all that's left. So let me just do a quick 90 seconds. It has better visuals than well, it has visuals. Sorry, I had it loaded up and then I had to restart the computer. Oh, come on, where did you go? Alright, let's try Firefox.
PET scan, CAT scan, they're both non-invasive.
Was it with you guys that I had this issue the other day? Or was it the other section? I'm having a problem with the views on my, like all of a sudden out of nowhere with the views on my laptop. I hate this thing where you have to slide over like off of your screen to get into the other display. What's the easy fix? Cassie, what is it?
You can turn off, or, I think if you go to settings and like display, it's in there.
I would love to just fix this once and for all because I've been having this problem all week. All right, you want me to do what? What is it? See, what's funny is that is not even on my screen. Like, I mean,
On my computer, there's an easy button.
yeah, I thought, I used to think there was an easy button on here too, but I can't find it. All right, anyway, let me just slide it over. Whatever.
Option.
It's actually not that big. It's easy if I'm just looking this way. It's easy. Except now I can't find my. Oh boy. That's right. I don't need that button, right? I don't need the mouse pad. Let me go backwards. Okay, I do need the mouse pad. Alright, if I can see it here, I gotta slide it all the way over here. There it is. Wow, that's
Invasive diagnostic tools a doctor will use to look inside the body. They're both used to pinpoint cancer, but have very different objectives and methods.
So PET scan measures activity within a cell. Okay, it doesn't have to be cancer, but cancers tend to be more active in the surrounding tissue.
PET scan stands for positron emission tomography. It uses sugar marked with a radioactive molecule. Active cells consume sugar and therefore are able to be tracked.
So they will then concentrate or absorb a lot more of that radioactive molecule, and it will sit within that cancer for a period of time. And then using a camera, we can see where that radioactivity is.
While the PET scan allows doctors to distinguish between living and dead tissue, the CAT or computerized tomography scan offers a different perspective.
CAT scans, for example, measure density. And if you have something in, for example, the liver,
The CAT scan detects changes in the body structure, such as the size, shape, and exact location of an abnormal growth.
so when I see somebody that has either breast cancer or colon cancer or lymphoma or many other malignancies, you want to make sure that you have a clear understanding of where their tumors are.
Alone, each imaging test has its benefits and limitations, but by combining these two state-of-the-art technologies together, doctors can more accurately diagnose and monitor cancer. For Lee Memorial Health System, I'm Amy Osher.
All right, so this positron, electron annihilation of mass, right, happens all the time. All the time. Great. Now how do I get back to the other view? Escape. I did. I hit escape like twice. Oh. All right. Actually, I found something that I didn't find before, but it didn't work. All right, any other bright ideas? I hit escape. Unplug it from the projector, then plug it back in. Yeah. It's probably going to be the...
Google how to disable.
Yeah, right?
So it's to the bottom right hand corner of the YouTube. Yeah, see if you can.
I don't even know how to get there. Here, let me... Oh. How do I get to it?
Just scroll off the screen focus.
There, like that.
It's like I have two monitors, stuff like that.
Right, fine. This? No, it didn't do anything. Oh, it did something. Just, just took it out of full screen.
It should be in the settings on the display.
Alright, whatever. Whatever. Don't need the projector.
We get extra credit for coming up with this.
You didn't come up with a solution. If you had a
We researched
solution
it.
that
We
had
researched it.
prevented all this waste of time already, I'd be in the business of extra credit. So, I made reference to a different unit of mass earlier that I like better than the unified atomic mass unit. And at first glance, you're not going to like it. Right? You're going to hate it. But you're really going to like it, it might not be till next class. That different unit for mass comes from our Einstein mass energy equivalency statement. But we isolate for mass. Right? So all we got to do is divide each side by the speed of light squared. Right? Boom. So mass is the equivalent of energy divided by speed of light squared. Now, what is our normal unit for energy? Joules, I heard it, right, joules. But a different unit that we worked with in topic 5, and now we're going to work with a lot for the next few classes, is electron volts. Okay? So, and really, an electron volt isn't very large, so we're not typically going to deal with electron volts, we're typically going to deal with mega electron volts or giga electron volts. But the preferred unit of mass here is a unit that's called electron volts per c squared. Or again, more commonly, we're going to deal with a unit of mass called the mega electron volt per c squared. And there is a conversion, right, in your data booklet for getting from atomic mass units to MeV per c squared. And I suppose you could also go from kilograms to MeV per c squared. The beauty of mega electron volts per c squared is we're not going to have to do any conversion, but we might not actually see that until our next meeting. So for right now, right, I'm just saying that we also could measure mass in any unit of energy divided by or per c squared, right? And then we'll see why that makes sense in maybe later today or next time. When we do end up using this unit of mass, we don't really ever end up putting in the value for the speed of light, right? We just leave it as per c squared. That's why this ends up getting super helpful. All right. So we're going to come back to that, right? So the last objective was to apply the Einstein mass energy equivalency statement. We haven't actually done that, but we did say what the Einstein mass energy equivalency statement was. Our next objective was define, and it was a bunch of different terms. And the first one was called binding energy. I'm going to give this a shot and see what happens when I turn this back on. So we know that all of our relatively stable nuclei, and I would call any nucleus that we can actually jam together and keep for at least a few seconds, right? I'll call that relatively stable for right now. Any relatively stable nucleus has lots of strong nuclear force. We have some electrostatic repulsion. Get one that at least makes some sense. That has 4 protons, 4 neutrons. That's pretty good. I'm just going to devote another few seconds to it. Now I'm kind of obsessed.
What software?
We try
What
option.
software? Well, I'm trying to use Power.
I mean, like the computer.
Mavericks.
Okay.
Try
Nah. Okay. Whoa. I did it.
Oh, really?
No, it wasn't F3.
Oh.
I actually don't know how I did it.
Did you put it in full screen?
I'm not going to question it. No. It was already there. All right. Wow. So binding energy, right? That's what we're working on. We already know that it's only due to this strong nuclear force that we're able to have anything, more massive than a proton. Right, so if we have a stable nucleus, then we have a lot of strong nuclear force, which is able to counteract our electrostatic repulsion. And that nucleus is pretty happy, right? So if we have a stable arrangement of nucleons, right, they're happy how they are. If we want to take that nucleus apart, we need to do some work to it, right? If we want to get in here, pluck out this proton, pluck out that neutron, pluck out this proton, we're going to have to do a lot of work. Right? We're going to have to use a lot of energy in order to pull them apart. And that's what this binding energy refers to. It's the energy required to take apart a nucleus. That's not a perfect definition. A perfect definition would be the energy required to completely disassemble a nucleus into its individual nucleons. That would be a perfect definition. Right? So this energy that's required to do that, we call the binding energy. It's a very important concept a very important quantity for the rest of this topic. Why am I getting repeats now? All right, so that was one term in that defined objective that had like 3 different things there. The next one is something called mass defect. Okay. So here we have, who is that?
Alpha.
That's a helium nucleus. It's an alpha particle, right? And if I want to pluck, the neutron and the neutron, or the neutron, the proton, if I want to pluck them apart, right? We already know we have to do work. We have to put in enough energy to pull them apart. We call that the bonding energy. What we find when we pull them apart is that the mass has changed. Okay? So the mass of this helium nucleus is not the same as the mass of our 4 individual nucleons once we pull them out of the nucleus. The work that we did, the energy that we had to put in to pull those nucleons apart, changed into mass. Right? The work that I did to pull these apart, right? We can't destroy energy. Energy is a conserved quantity. So the form of energy, once I do work to pull those apart, we have created mass. Right? We've used up other forms of energy, right? My chemical energy to do the work, and that energy is now in the form of additional mass of those nucleons. So this picture with the X, right, that's making reference to the mass, right? The mass does not stay constant. The mass increases when I pluck those things out of the nucleus. And that change in mass, that difference in mass between our assembled nucleus and our individual nucleons, that's known as the mass defect. And our symbol for that is a delta M because it is a change in mass. Okay, yep. Weird stuff. Remember, I told you last year, mass is not conserved. Right? In chemistry, you're told mass is conserved. That's fine. When we start messing with the nucleus, right, then mass is absolutely not conserved. Okay, so here's a different way to look at it, and here's a better way, right? We have, who do we have this time? Maybe that's 3 protons, 4 neutrons. What is that, beryllium? I don't remember who has 3 protons. So we have an assembled nucleus, right? We do some work, we add energy to this nucleus to pull it apart, and that energy that we added is now in the form of mass. So all of the nucleons now have a greater mass, right? More MeV per c squared, more atomic mass units, more kilograms than they used to. Okay? So the mass of individual separated nucleons is greater when they're separate than when they are together in a nucleus with our strong nuclear force. And those individual masses are what's in the data booklet. All right, so right above where we were just looking with our atomic mass unit, where it gives proton, neutron, right? That's for unbound protons and unbound neutrons. I'm happy to pause. We're not nearly done with this yet. But follow-up questions right now. All right, so the recap is, if we want to disassemble a nucleus, we have to do work. We have to add energy to that system. Right? We call that the binding energy. And that energy transforms into mass. Right? So that separated nucleons, once we pull it apart, are more massive than a separated nucleus. So we're going to solve problems, right, with binding energy and mass defect. The only equation we use is the equation in the data booklet, that Einstein mass energy equivalency statement, right? The E equals mc squared. We just write it a little different, right? The E is a binding energy, and instead of m, we just use our mass defect. So we can interrelate how much energy we put in and how much mass gain we get. The only other quantity we need is the speed of light. And sometimes we might do these problems in kilograms, but if we're lucky, we're not going to be doing them in kilograms. So let me model one problem for you with kilograms, and then we'll look at a couple of others in other units of mass. All right? So in this problem, we have a standard helium nucleus. And I'm telling you the mass of the nucleus, right? That should be enough information along with the data booklet to find the binding energy of helium-4 and the mass defect of helium-4. And our starting place is going to be the mass defect. And to find the mass defect, right, we already know the mass of the assembled nucleus. Now we need to find the mass of the separated nucleons. All right? So we're going to need our data booklet for that. I would highly recommend that you get this pretty neatly in your notes so that you can model future problems after this. All right, so the first thing that I'm going to write is the mass of the nucleus. Right, which is a helium nucleus. And that is 6.6447 times 10 to the negative 27th kilograms. All right. Now I need to find the mass of my separated out 2 protons and 2 neutrons. All right? So I have 2 protons, 2 neutrons. I need to know what is their mass when they're outside of the nucleus. So I'm going to go to my data booklet, and I'm going to use the mass of a proton. Now they give it to me in 3 different units, all of the 3 units that we talked about today. For this problem, I'm going to use kilograms, since that's the unit that I gave you for the mass of the nucleus. So for an individual, so we have 2 protons, right? So I have to multiply the mass of a single proton by 2, and that is 1.673 times 10 to the negative 27th. All right, so I'll get that on my calculator, but before I do that, let me set myself up to be able to do the neutrons also. So we also have 2 neutrons, and my data booklet says that the neutron is a hair heavier, like, I don't know, about 0.1% heavier than a proton. So I'm going to get both of those, and then I'll add them together to have the total mass of separated nucleons. And I highly recommend, so not only certainly get this in your notes, but I think you should probably do the calculation along with me. And I do want to try and keep track of significant digits. So I am getting a mass for my separated nucleons that is a little bit more massive than the aggregate, than the nucleus itself. So let me pause for 20 seconds while folks catch up. All right, so far, I know the mass of the nucleus, and I know the mass of the isolated nucleons. Questions from anybody on arriving at the mass of the isolated nucleons? All right, well, the mass defect is just the difference between the 2. All right, so for the mass defect, I just literally subtract that. 6.696 times 10 to the negative 27th minus 6.6447 times 10 to the negative 20.